Can you hear me?
Yes.
Well, thank you, Pat, Holly, Aaron, Glenwood Park Village for having me. Thank you for coming back. I guess I didn't scare you off completely last time. This is actually part 2 of what I talked about last time. And I'll recap it in just a second. But just following up for a conversation I had a few minutes ago, the point here is that every culture, every religion has an account of how the world came to be and how we came to be, actually, the people. These are fascinating stories in and of themselves. Many intuitions, which according to science, but science, through careful observation and data collection and mathematical analysis, has over the past 100 years, it started almost exactly 100 years ago, has come up with an account of the origin of the universe that is weirder, more counterintuitive, more mind-blowing, every adjective you can think of, than anything that the legends and mythologies would have us believe. I ended up, of course I've known about this for a long time. A couple of years ago, and this is a story I'll leave for the Q&A if anyone is interested, I ended up writing a book by accident on this subject. And it's called Cosmic Origins. And what I found when I was writing this, it started out as a short article and then it turned into a book. And the reason it turned into a book was because I realized that as I delved into it, I sort of knew the basics of what had been discovered, but it's a fascinating human story. And it wasn't one big eureka moment. It was a lot of very human, very smart, but very human scientists struggling to understand what they were seeing. This isn't a story they sat around one day and made up, says, God, I don't know if we could sell it. They were basically hit in the eyes, in the face with facts they couldn't get around, try as they might in some cases. So, last week we talked about, well, here's the story so far. Okay, I've seen Drama in the Galaxy, it's a modern picture. You there? Yeah. The scientific revolution, which started in 1543 with Copernicus and his theory about the Earth orbiting the sun, one of the key insights there was the realization that the planets are other worlds, these dots of light that move across the sky, planets, and the stars are other suns. Just think about that, just how profound that is. And we learned last week that an astronomer in the 1920s named Edwin Hubble, this is how you get a space telescope named after you, discovered that these funny spiral nebulas that astronomers have been observing and arguing about were in fact other galaxies just like our own. That had been a big debate. He settled it, with some key observations. It was also apparent in the scientific revolution, and particularly Isaac Newton and people like Galileo and such, that the heavens and the earth are one. That is, the heavens are not some exotic quintessence stuff that is utterly different from anything here on the lowly, messy earth. It's the same stuff. And in fact, a technique called spectroscopy, looking at the light and looking at the colors of the light from celestial bodies. Through that, you can compare it to what you see in the laboratory. You realize that the stars and the nebula and the planets are made of exactly the same stuff as we have here on Earth. And that's not a hypothesis, that is, you can demonstrate that. Scientists also, by the 1700s, realized that the universe is not only very large, it's very old, millions if not billions of years old. You can see that by the strata and geologic strata. But Hubble, again, demonstrated, he looked at this galaxy right here, the Andromeda Galaxy. He saw that it's made of stars, and he estimated the distance. And the modern, I think it was an underestimate, but the modern distance is 2.5 million light years away, which means that the light that went into that photograph left Andromeda and traveled for 2.5 million years to get here, and left about the time a creature named Homo habilis started wandering around in Africa. That's how long, and that's the closest big galaxy to us. The rest are further away than that. So the universe is really big. And not only that, it's growing. The universe started from something smaller and it's expanding. Hubble found that too. There's a reason we named the Space Telescope after him. It's expanding, and as the universe expands, it's carrying the galaxies along with it. Okay, now we're going to look at one which you would think is a logical consequence from this fact. If it's expanding now, you'd think, well, it must have started small and had an origin. It started from a very different beginning. It started, as this thing. What we now call the Big Bang had to be, but there was huge resistance to this idea. Most astronomers, Einstein on down, hated the idea of the universe changing over time. They wanted a sort of stable, static universe. They rationalized it in many ways, but in fact, there was so much resistance to this idea that what we now call the Big Bang, the origin of the universe, had to be rediscovered 3 times before it finally took hold. So the first discovery in the early 1930s took the form of a letter to the editor. It was the editor of Nature magazine. But the story starts with this fellow, a stern-looking gentleman. Actually, he wasn't all that stern. But his name was Arthur Eddington. He was an English astronomer at the University of Cambridge. And he, among other things, is known as the man who made Einstein famous. How did he do that? Well, in 1915, when there was a small dispute going on in the middle of Europe, the German scientist named Albert Einstein came up with, well, he was already famous with his theory of relativity. He came up with what he called general relativity, which was also a theory of gravity. He says gravity has to do with the curvature of space and time. I'm not going to try to explain that.
That's the next session.
But this was an obscure theory, and after all, there was a war on. But in 1919, there was an eclipse that if Eddington led an expedition to observe the eclipse on the island of Principe, however you pronounce that. Anyway, it's off the coast of Africa. And the idea was that Einstein's theory of gravity had predicted that light itself has a kind of weight, that if the light from a star, as it went past the sun, would be visibly deflected because the light gets bent. It's like a satellite trying to go past it. It's affected by the gravity, and he predicted how much it would be, and Eddington, among many other people who also observed, and he photographed the stars that you could see right during the eclipse, and damn, if it was exactly what Einstein predicted. Now, this news spread like wildfire. It was written up in the New York Times. There was a little article. This weird theory, this weird-looking German astronomer, and it was important that he was German because we're sort of doing cross-cultural things now after the war. Had predicted it, and Arthur Eddington was one of the people and most prominent astronomers who had demonstrated that. He really understood his math. Eddington, and a few years later, wrote the first textbook on Einstein's theory, helped make it something that many people could understand, many other physicists and astronomers. But what we're going to talk about today is a lecture he gave in January of 1931. He was speaking to a group called the Mathematical Society in England. And the title of his lecture was The End of the World from the Standpoint of Mathematical Physics. Now, what he meant, it's a very long lecture. I mean, people must have had iron butts to listen to this. But he discusses in great detail how physics accounts for time and the nature of time. And there's just lots to it. But when he said the end of the world, that means if you think of time as a line, it could have two ends. It could be in the far future, or it could be in the far past, beginning. And he had this is a direct quote. Philosophically, the notion of a beginning of the present order of nature, that is, the universe as we know it, is repugnant to me. He admitted it, that it's a logical possibility, but the problem is you can't study the origin of the universe by science. I mean, it's just not accessible to you. It was a long time ago. And besides which, if you start talking about the origin, then here's the inevitable question, what comes before that? Where did the origin come from? Actually, that's still one. But anyway, so Eddington was so prominent that his speech was published in Nature in March of 1931. Nature is sort of the flagship British journal. Still is. And it was read by a youngish fellow, a Belgian priest and physics professor at the University of Leuven in Belgium named Georges Lemaitre. Now my French is terrible, so I probably mispronounce his name. But Lemaitre was already the man who had predicted Hubble's discovery. Now Hubble, remember, had discovered that the more distant a galaxy was, the faster it was rushing away from us. And nobody knew what that meant. But Lemaitre had actually predicted this a few years before Hubble published. And he had written a paper, and in English, this was 1927, what he had done is he'd taken Einstein's equation, gravity, curvature of space, applied it to the whole universe, and gotten a solution that described the evolution of the universe. And he discovered that it had to be either expanding or contracting, and he worked out, among other things, the title of it in English, A Homogeneous Universe, the same everywhere, of constant mass and increasing radius expanding, accounting for the radial velocity of the extragalactic nebula. That is, he had explanation for why those galaxies seem to be rushing away from us. Now, the problem is it wasn't in English. It was in French in an obscure Belgian journal, which nobody read. Nonetheless, he went to a conference later that same year, 1927, which was also attended by one Albert Einstein, who was the most famous scientist in the world. He must have been in awe. Einstein listened to his Lemaitre's discussion and basically told him, your math is fantastic, the physics is abominable. The conclusion just you got to find a different solution. Basically said. And besides, Einstein told him, you weren't the first to derive these equations. A Russian named Alexander Friedman did this in 1924. Now you can imagine how Mitch must have felt, just crushed. Anyway, he went back to the University of Notre, kept quiet for a few years, but he had a certain reason for self-confidence. After all, he had studied with Eddington himself in Cambridge, and for that matter, if you perhaps remember, there was a fellow named Harlow Shapley who also made some profound discoveries. He had just taken over the Harvard College Observatory. Lemaitre had studied with Shapley there. And when he saw Hubble's paper describing, this redshift with distance, these expanding galaxies, he sent his paper to Eddington, who he knew was a very sympathetic and mentorish kind of guy. And Eddington became, this was in 1930, he sent it, and Eddington became his ardent champion. He talked up Lemaitre's work. He arranged for this thing to be translated and published in English and a prominent journal. And it just basically made Lemaitre's reputation. And in fact, that English version came out at pretty much the same time as he read Eddington's speech in March of '31. So Lemaitre had every reason to be deferential and to Eddington and not rock the boat. And he'd been effectively slapped down by major physicists before. Nonetheless, he wrote a letter to the editor of Nature. There it is. That's the entire extent of it. That's about 700 words. You can't read it, but the title there is The Beginning of the World from the Point of View of Quantum Theory. By the way, this photograph right here, insect remains in the gut of a cobra. I love scientific journals in this era because they just got all this stuff. Anyway, what he says in there, obviously we can't read it, he was respectfully disagreeing with Eddington. He recalled the repugnant comment and basically said that the early universe must have been a different order of nature, not the present order of nature, but different. How so? Well, let's imagine that the universe it's expanding now, so let's imagine we run the movie backwards. And so everything rushes together towards the beginning. And eventually, as you get close to the initial instant, everything, all the matter in the universe would have been crushed together. He didn't say it this way, but that's essentially what he was saying. Crushed together, and his idea, well, maybe it was something like, we don't know exactly what it would have been, but something like some gigantic atomic nucleus with all the mass of the universe, so that and that would have been the beginning. And if you run the film forward again, then what we'd see is the nucleus would decay in some kind of radioactive way and form all the particles that we see around us today. Now, we're going to see in a few minutes, that wasn't quite right, but it wasn't entirely wrong either. He also said, sounding very modern, because this is still an issue in physics, at the point of origin, t equals 0, if you look at the equations, at t equals 0, that's an awkward point because the curvature of space and time becomes infinite there and the density and the temperature become infinite. And basically time stops. If you ask what comes before that, it's like asking what's south of the South Pole. It just isn't there. This is still, physicists still argue that that some other type of physics has to occur. We don't know what it is. But anyway, he said space and time would cease to have any meaning at that point. So that was his conclusion. That was basically what he says here. And he makes one other point, and this is implicit in what he said, not explicit, but it's very important, that the birth of the universe followed natural law and could be studied by the methods of science. Since he was a priest, it's probably important to point out that he didn't mention Genesis in here. There's absolutely no hint of religion. Waldrop was adamant throughout his entire career, his entire life, that science and religion are compatible. They are just different aspects of the same reality. And he saw no contradiction. He didn't do a literal interpretation of the Bible. But he said all of this could be studied by the methods of science as natural law, God's natural law, but nonetheless. He expanded upon these ideas a few months later in another essay. There was other people contributed as well. It's a collection of essays about the origin of the universe. And he had made two additional points. That the cosmos was born hot, grew fast, and cooled as it went. And he had this wonderful phrase: because of that, today's universe is the ashes and smoke of bright but very rapid fireworks. Which is pretty much true. It's also a beautiful phrase. And he had another point, which was that all this commotion at the beginning of the universe would have left some sort of afterglow, some sort of radiation that we could still see today. This would have continued as the universe expanded. And he thought it was cosmic rays, which were these particles that come piercing down to the atmosphere. He was wrong about that, but his intuition, basic intuition about an afterglow, as we'll see, was correct. Now, these ideas got actually a fair amount of attention in the 30s. A few months after this came out, he got a big write-up in Popular Science. This Belgian priest has got this great idea about the origin of the universe. He wrote his own longer article in 1934, which sort of summarized all this. So the ideas were around. On the other hand, there was as I said, there was a lot of resistance from scientists, including both Eddington and Einstein. They didn't ghost him or refuse to talk to him. It was all very cordial, but he just didn't agree. In any case, Waldrop kept on working in cosmology, but he was also teaching. He got elected to the Pontifical Academy of Sciences. He did a lot of research in cosmic rays, and I won't be able to follow his story any further till the end. But in the meantime, also in the 30s, actually reaching back earlier than that, we had the second discovery of the Big Bang, which, as often happens in science, it started with a seemingly unrelated question. What makes the stars shine? There's the sun. The sun is a star. There are the stars. They're glowing. They've been there for millions, if not billions of years. At the time, nobody knew. The current figure for the age of the universe is 13.8 billion years, by the way. The sun is 4.6 billion years old. as is the Earth. But it was a big mystery at the time. How could they possibly keep putting out all that light and energy for all that time? I mean, they obviously weren't burning like a candle flame. There's no oxygen in space, and besides which you could calculate it would have run out of fuel long since. People came up with all these ideas, none of which quite seemed to work. And the key idea came again from our boy Arthur Eddington, this time in 1920, another lecture. He gave a lot of lectures. Another long lecture that was published. He had the idea that the source had to be what he calls subatomic energy. Whatever the source of like radioactivity was, or things like that. It was a bit hand-wavy, but he said, okay, here's an idea of how it might work. And he pointed to some recent laboratory measurements that measured the mass of the nucleus of the helium atom. And helium is the second lightest element. And compared it to the mass of the nucleus of hydrogen, which is a particle that very year had gotten the name proton. Eddington realized that the mass of the helium atom, or the helium nucleus, is ever so slightly, just a fraction of a percent, less than 4 times the mass of hydrogen. So, here's his idea. Suppose at the core of the star, where things are really dense, really hot, it's crushing these hydrogen nuclei together, and 4 by 4, they form helium. Now, what happens to the leftover mass? According to Einstein, E equals mc squared there, mass is a form of energy. Energy, physicists will swear up and down, is conserved. You can change its form, but you can't increase or decrease it. So that energy, what that mass had to show up as energy of heat and light and fast-moving radioactive particles and so forth. Now, as it turns out, this was just a sort of hand-wavy hypothesis of his. He was absolutely right. It would take 2 decades and some major advances in nuclear physics to pin that down, but that's exactly what happens. I assure you, when they got the details, that arrow is a lot more complicated than what we're showing right here. But that's what's happening in the sun. That's what's happening in stars. But along the way, there was, by the way, and this process is now, he said in his lecture, if that were the case, then we need to look no further. There's plenty of energy from subatomic energy. Today we call it thermonuclear fusion. But there was a problem before you could really nail this down. And that problem was there's not enough hydrogen in the stars, or there didn't seem to be. Remember last time we talked about you could analyze the light from stars, and you see that some wavelengths are missing. These are called spectra. And when you look at the stars or any hot gas, you see that some wavelengths are missing. In fact, you can use this these correspond. You can map that to what you see in the laboratory and identify which elements are there, and how hot the star is, and actually the amount of elements that are there. Now, these are different types of stars that are from hot to cool. The sun is right here in the middle. zero star. And the problem is when you did that analysis, at least just to look at it, there didn't seem to be that much hydrogen. You know, you couldn't, Eddington's theory wouldn't work because, you know, there wasn't enough hydrogen to do it. In fact, they thought, you know, the stars were roughly the composition of the Earth, which meant lots of iron, lots of calcium and silicate rock, essentially, and not much hydrogen. Well, okay, so this young woman corrected that. Her name was Cecilia Payne, and after she got married a few years later, she signed her papers, Cecilia Payne Koshkin. And she was born in England, grew up in London, and in 1925, she wrote at Radcliffe the most brilliant PhD thesis ever written in astronomy. It was also the first PhD thesis ever written in astronomy by a woman in the US. Now, what happened? She grew up in London, as I said, and at age 18, she was talented in just everything she tried, just a real fireball. At age 18, what we would call high school, she was so talented in music that she was urged to become a professional by Gustav Holst, if you know, is one of the major English composers. But no, she was interested in science, so she got herself a scholarship to Cambridge, not easy to do. And in 1919, she went to hear Eddington give another lecture, this time about his eclipse expedition, which had proved Einstein. Payne was so excited by that lecture, she went back to her rooms and wrote down the whole thing verbatim in longhand. And when the lecture was published later, it turned out she got it almost perfectly. In any case, she got to know Eddington. He became a mentor, just as he would for Mitch later on, and many others. He championed her, encouraged her in her science. But of course, in those days, a woman could not get a degree in astronomy or physics or anything like that. So Eddington provided her an introduction to Harlow Shapley, who we knew very well. And Shapley, over at the Harvard College Observatory, had just established a fellowship to bring women into astronomy. And so she got one, and she came over to the other Cambridge in Massachusetts. And then Shapley, she was such a standout that Shapley supported her effort to get a PhD, which no woman had ever gotten a PhD in astronomy. This was against considerable opposition in the field. She was determined, so was Shapley. She got the PhD from Radcliffe in 1925, and the subject was interpreting spectrum. And she says, look, you got to do the analysis right. You got to, it's messy. You got to look at the temperature of the star and the pressure and the gas density, and you know how the stars absorb light, how they emit light. It's just incredibly complicated. The thesis was 215 pages, and she did all the calculations without a visual computer. And her conclusion was, if you do the analysis right, there is lots of hydrogen in the stars, more than anything else. So there's no problem keeping them fueled, but that just led to another mystery, which is this. This is the cosmic recipe. Once you start doing the analysis right and looking at all those stars, and the gas clouds and so forth, you look at young stars, old stars, newborn stars, gas clouds floating in interstellar space, so forth. You do the analysis and you keep, on the average, not the planets, because those are like little rocks, pebbles floating But you look at the analysis of the overall composition of the universe, and that's what you get. That blue stuff is hydrogen, 75%. The red stuff is helium, the second lightest element. That's almost 1/4. And then everything else, the yellow is, I couldn't get the graph to do it, but the yellow is oxygen, which actually turns out to be relatively common. And then the green thing slices everything else. You know, the nitrogen in the air, the silicon in the rocks, the iron in the core of the earth, all of that, that's just that little sliver. And the question is, why? Where does that come from? Sure, some of the hydrogen gets turned into helium when the stars shine, but not nearly that much. And so you got to explain that. So, and the ratio, that's sort of 3 times, 3 to 1 is the ratio. How do you explain that? Well, the guy who finally cracked that, or instigated that, was a fellow named George Gamow. Well, those days he was called a Russian. Now he'd be called Ukrainian because he was born in Odessa. And he had quite the career. He studied in Leningrad with Friedman, so he learned his relativity. In the late 1920s, he made major contributions to the theory of the nucleus. In the early 1930s, he realized that things were not going well inside the Soviet Union, so he fled. He and his wife, who was also a physicist, he said later that in 1932 they first tried to kayak across the Black Sea to get to Turkey, turned back by bad weather. Then later in the year they went up to Murmansk, which is up in the Arctic Circle, tried to kayak across the Arctic Ocean. That didn't work. Bad weather. But then in 1933 they both got invited to through some miracle, to a scientific conference in the West. The authorities let them go and they never looked back. He actually wound up right downtown in George Washington University. One of many. He, in the 1930s, while at GW, he helped work out fusion and stars. Remember, as I said, it was complicated. And then after DNA was discovered in 1953, he turned his attention to trying to work out the genetic code. He had this elegant mathematical theory that was beautiful but wrong, but okay. He was also quite the science popularizer. He wrote books I remember reading as a kid, 1, 2, 3, Infinity, just talking about science. Very famous for that. But what we're going to talk about today is that starting in 1946 and going out until the DNA thing, he looked at element productions in the Big Bang. Well, it wasn't called the Big Bang then. And he got 2 graduate students. Their names were Robert Herman, who was from New York, and Ralph Alford, who's from right here in DC. He went to Theodore Roosevelt High School over on the east side of Rock Creek Park. In 1946, he kicked the whole thing off. Everybody was getting back to research after the war. And apparently he didn't know about the matrix work, but he pointed out in a paper there, a very short paper, that the universe that are that small, it was a hot, dense fog of neutrons and protons, and it expanded fast, which is what the Lemaitre had said. But Gamow concluded it himself. In fact, it was so fast that this fog of neutrons it was like a spray can, it gets very cold, or snowflakes, condensing in a cloud, but that turning into water first. It just crystallized. So this fog of neutrons crystallized into snowflakes, chemical elements, just as fast. The technical term is it wasn't in thermodynamic equilibrium, but never mind. Then a paper he wrote with Alpha, he says, well, if you take this picture and do a rough estimate using nuclear reactions, what we know about nuclear reactions, you actually get a decent fit to the observed abundances of the elements, including, this actually came out Alpha's PhD thesis, you could get that 3-to-1 hydrogen to helium ratio that fell out quite naturally. That was what you would expect from this sort of crystallization process. They couldn't get the heavier elements. Now, this particular paper is one of 12 this group wrote in 1948 on the subject. But this particular paper was the first of that 12. And it's famous for another reason. It was written by Alpha and Gamow, but Gamow, being an inveterate jokester, inserted as an author the name of his good friend, who was named Hans Bethe, a German refugee scientist. And without telling Hans at all, so that when you read out the author list, it's Alpha, Bethe, and Gamow. That was his idea of a joke. Bethe thought it was pretty funny. Alpha was kind of ticked off. But anyway. At any rate, so with no nuclear physics, they worked out the details, again, without digital computers. Very complex, but they couldn't explain the heavier elements, they could explain the 3-to-1. We now know that the heavier elements were made later on in the stars. So they're a little disappointed. But one of the papers, it was written by Alpha and Herman, two grad students, in 1948, and almost as an aside, they were discussing something else, there would be an afterglow from all this. And it wasn't cosmic rays, it would be electromagnetic radiation, photons. And these, when you worked it all through, there would be these very low energy photons, microwaves, in the microwave region of the spectrum. There's, they sort of calibrate these things by temperature, and it would just be a few degrees above absolute zero. They couldn't get the right number, but they were just estimating. And that was just like almost an aside at the end of one of these papers. Okay. Now, let me back up. This work, didn't fall into obscurity exactly, but there weren't a lot of cosmologists back in those days. And they, most people working in this field were doing it part-time, sort of as a hobby. All these guys went off to do different things. And so, you can't say that it was forgotten, but there was a huge amount of attention paid, in part because there was a lot of attention paid to a theory that showed up same year in 1948 called the steady state theory. And this was one of the leaders there. It was cooked up by 3 young Cambridge University physicists who hated the idea of the cosmic beginning. The leader of this group was Fred Hoyle, a British astronomer, physicist. Now, how can the university, that they couldn't deny the reality of the expansion, so how do you account for the expansion? So they said, well, maybe as the galaxies moved apart, new matter was just popping into space all over the place to fill in behind it, presumably hydrogen. And over time, gravity would pull these newly created atoms into new stars and galaxies to replace the old. So it was sort of, the universe is sort of like a river. It's always flowing, yet it's never moving. Always expanding, never changing, and you wouldn't have to talk about an origin. They were just viscerally convinced of this. Now, hey, it violated the conservation of energy, but it was elegant. And for about a decade and a half, this idea was taken quite seriously. And besides, Hoyle was quite the popularizer himself. He talked it up quite a bit. And the reason we're actually talking about him is because in March of 1949, he was on the BBC. They invited him to give a radio lecture about science and cosmology, his choice. And during the course of that lecture, he said the following: these theories, by which he meant evolutionary cosmology with an origin, were based on the hypothesis that all matter in the universe was created in one big bang at a particular time in the remote past. That's the first time anybody had ever used the phrase Big Bang. Now, Hoyle later tried to claim that he didn't mean it to be disparaging, just as a description. But that's BS, because a few minutes later in the same lecture, he said, this Big Bang hypothesis is irrational and cannot be described in scientific terms. So he used it pretty pejoratively. Anyway, he was instrumental in helping show that the heavier elements were made by stars. The steady state sort of lasted for quite a while. But what eventually killed it was the discovery number 3. Big Bang afterglow. This one place to start this story is with a fellow named Robert Dicke, who's the physicist at Princeton. He had worked on radar and associated technologies at MIT. He didn't care if the steady state of the Big Bang was correct. He was just tired of listening to people argue about it. So he decided to settle with data. He had helped pioneer microwave detectors. There's something called a Dicke detector, which is still used. Very sensitive microwave detector. He did a whole bunch of high precision tests of Einstein's theory, which it passed with flying colors, by the way. But in 1964, he said, okay, we got these microwave detectors. Let's find the Big Bang afterglow. He didn't know about Gamow, he didn't know about the Nitro, apparently. But he did figure with all that commotion, there must be something left over. So let's look for it. So, he had 2 students named Peter Roll and David Wilkinson. I couldn't find good pictures of them, I'm sorry. And he assigned them, okay, build the detector, build the antenna, and so they went to work in the lab, and they were happily building all that. And he had a 3rd student named James Peebles. You work out the math, that is, figure out what we're actually looking for, do the Einstein's equations and so forth. Now, he didn't know about Gamow and so forth, and Peebles happily went to work. They all happily went to work, and they were making great progress. And then Peebles, calculated, element distribution, microwaves at a few degrees above absolute zero. Kelvin is what it's called. And then he happily sent it off to a major journal called the Physical Review. And the editor said, nope, it's been done, 1948. Peebles was embarrassed. Dicke took full responsibility. Says, I should have found that. We should have known about that. Nonetheless, it was just embarrassing. So they kept going, and People kept calculating, and they kept building the antenna, and they were sure they were way ahead of everybody else. If it's out there, and if it's what people think it's going to be, we're going to be able to detect it, and we're just going to scoop the world. Well, in February of 1967, they had their regular Tuesday lunchtime team meeting in Dickie's office. Dickie gets a call, and they chat, and by the time he's finished, the three are just silent. And Dickie says, "Well, boys, we've been scooped," and they had, by accident. About 30 miles to the east, in Holmdel, New Jersey, at the Bell Labs facility there. These two guys, Robert Wilson and Arno Penzias, were Bell Labs employees. There was this old antenna, that's it in the background, that had been used for satellite communication, and it was just sitting there. And so these guys were going to refit it for radio astronomy. In those days, Bell Labs did a lot of basic science. And they just had to clean it up and get it all ready. And they were going for extreme sensitivity, so they had to eliminate all interference. Making sure that there were no stray radar signals in the Air Force or radio signals. They had to clean out pigeon nests, or as they put it, we had to clean this white dielectric substance off the detector. And the problem is, they've worked on this for like months, better part of a year, and they kept detecting this hiss that wouldn't go away. And it was just this hiss in their detector. And they figured it had to be a glitch somewhere, but no, they tested everything. There was not a glitch in the instruments. They checked, it's not coming from the sky, it's not coming from the ground, it's not coming from the sun, and they're double checking all this. It's not coming from the Milky Way. They couldn't figure out what it was. It was the same day or night. It was the same everywhere they looked in the sky. And they thought, something's wrong, we don't know what it is, until one day they saw a mimeographed copy, what they called preprint in those days, of Peebles' calculation about the microwaves from the origin of the universe. They saw that, and then they made a call to Dickie. I think it was Penzias who called. And they said, "We've seen this, and we think this is what you were predicting." Now, as Peebles later recalled, he's written the whole history of this. The three of them felt terrible for Dickie, and he felt terrible for them, because they had been scooped. Nonetheless, everybody decided to be adults about this. So in July of '65, they published back-to-back papers in the Physical Review. These guys published a paper talking about the observation. They didn't try to say what it was, they just said, we've seen this. And the Princeton team published a paper right after with the interpretation. This was the background hiss, the afterglow of the Big Bang. And that put the nail in the coffin of the steady state theory, because there's no way the steady state theory could account for that. Well, tried, but they couldn't. So that left the Big Bang. There are three pillars of the observation. There's the cosmic expansion, which it explains. There's the hydrogen-helium ratio, which it explains. There's the microwave background, that's the afterglow, which it explains, and it's all perfectly consistent. And Wilkinson and Lowell, once they finished their antenna, they carried it up to the roof of their building in Princeton, turned it to the sky, and they confirmed the result, which is pretty important in science. Penzias and Wilson, which shared 1978 Nobel Prize. Peoples would continue his career in cosmology, in theoretical cosmology, and he would share the 2019 Nobel Prize. He's still alive. Wilkinson might have shared one for observations of, he continued to research the microwave background, but he died before that particular prize was awarded, so unfortunately. Hoyle kept trying to come up with ways the steady state could work with this, and his ideas got crazier and crazier. That probably cost him a Nobel, because his work on the origin of the heavy elements, it did earn the Nobel for another part of the team that did it. And they probably didn't give it to Hoyle because his ideas by that point were just so off the wall. Gamow would be annoyed that they didn't get a citation in his papers. He went around muttering, but nonetheless he was remembered. And Lemaitre, by that point, was 71 years old. He was the president of the Pontifical Academy of Sciences. News reached him in June of 1966. He was dying from leukemia, but he was quite lucid. He knew he was hearing, and said, basically, it's wonderful news, praised news. So, in any case, that's how we discovered the Big Bang. This is way longer than okay, any questions? Yeah.
Yeah, I've read someplace, and don't ask me where, that the universe is expanding at a much faster rate.
Yeah.
What does that mean?
Well, it's so. There's, it appears, I mean, there's lots that goes into it, but if you look at the rate of expansion as you look further out in the universe, and when you look further out, of course, you're looking further back in time because the light takes time to get here. So what you're seeing is older and older. When you compare the expansion rate, way back then with what we're seeing now, it appears it's a subtle effect, but very real. It's been confirmed again and again and again. It was discovered in 1997 that the expansion rate now is a bit faster than it used to be. And so the expansion is accelerating. The question is why? And there are all sorts of ideas about that, and no one fully understands. There's a whole other talk to be, on the dark universe and so forth. People talk about something called dark energy, which is like this sort of cosmic impulsion that's doing it. I mean, mathematically it's pressure but negative, but anyway, never mind. It basically is pushing the universe, but very slowly. And so that's one of the current mysteries, what is doing this? We know this dark energy, this repulsion is out there. We don't know what it is, we don't know why it is. It doesn't fit with any of the modern particle theories. So it's a mystery. No, yeah. So I think you were next.
Did I understand you correctly that Wilson and Penzias confirmed the Big Bang Theory?
Could you repeat the
well,
question?
what they saw was certainly consistent with it.
Could you repeat the question?
Did Wilson and Penzias confirm the Big Bang Theory? They confirmed a prediction based on the Big Bang Theory. So what they saw is consistent. I mean, how do you prove anything? Essentially yes. After that, and after it was confirmed by multiple methods, by multiple people, the Big Bang origin became widely accepted in the 70s, which, by the way, is also when Big Bang started to appear in the scientific literature, the phrase Big Bang. Before that, nobody's going to be that undignified in the pages of a journal. Now it's just all over the place. But in any case, it took several years and a lot of confirmation, but we did it. Yeah.
So,
Sorry.
everything in the universe is expanding, including us.
No, not quite. Yes, the fabric of space and time is expanding, but we are held together by essentially chemical forces. The molecular bonds that hold our bodies together. And it turns out, we think of gravity as this really strong thing, inexorable, this curvature of space. But you know something? Okay, so that's that. I just outpulled the entire Earth. Okay? Gravity is actually the weakest force in the universe. We feel it because there's a heck of a lot of matter in the Earth, and that matter is creating gravity and holding us down. The individual galaxies, the Milky Way galaxy or our sun and so forth, they are not expanding. They are held together by local forces that for us here on Earth, it's chemical bonds or electrical forces, and they aren't participating in expansion. I remember last week I used the example of raisin bread, and imagine the loaf of bread expanding, but the raisins aren't expanding. They're just riding along with the bread as it goes. That's one of the first and most obvious questions, but no, we're not expanding.
So the edges are expanding.
It's sort of this space around us. The solar system isn't expanding. The galaxy is not expanding. It's just you got to go out to quite a large distance before expansion starts to become important. It's counterintuitive, but it's. Let's see. You had a question over there?
Yeah. What makes the sun a star? It doesn't look like a star. It's a little different.
It looks different than a star because it's much closer than. Much closer.
Closer.
Than any
Oh,
star. If you could go to the closest star to the sun is Alpha Centauri. It's in the southern hemisphere. If you went up to Alpha Centauri and got 93 million miles away, it would look the same size as the sun. And our sun would be this faint dot of light, off in the heavens somewhere. It's just far away. But in terms of its structure and what powers it, what causes all that light and heat, which is nuclear fusion in the core of the sun, it is a star, just like other stars.
Okay, thank you.
Let's see.
Oh, you okay?
You okay?
Go ahead.
If the universe is expanding, what is it expanding into? Is there something larger?
Excellent question. It is possible, and that was one of the first questions anybody asked. If you look at the space and time that we occupy, the 3 dimensions of space, one at a time, you can't see any other dimensions. You can't see the 5th dimension or the 6th dimension, except in fantasy novels. So everything seems to be rushing away. It is possible, mathematically, to make up a theory in which there are extra dimensions, and our universe looks like say a sphere, an expanding sphere. You can do that. But the question is, we've got no way to look outside our dimensions, to see other dimensions. Whatever happens out there isn't here. Anything we do here can't affect anything out there. So it's you can make up stories, but basically you can't observe it. Is what it comes down to. But that's an excellent question. There are theories. Superstring theory talks about space and time with 10 dimensions. Well, we have 3 space dimensions, 1 time dimension, that's 4. Superstring theory has 10. And so you can imagine, we're like a membrane or something in that space. But there's so far no evidence of it. And that's a mushy answer, and I wish I could give you a crisp answer, but basically we don't know. I'm sorry.
Earl?
Yeah, do I get a mic?
Oh, yes, go ahead.
Sorry about that.
No, she's finished. Thank you.
Thanks. My understanding is that at the beginning, light traveled faster than 186,000 miles a second.
That's one theory, yeah.
Okay, that's a theory. Now, when light is bent around the sun or any other large object like a star or something large, the velocity is still 186,000 a second. Is that the only thing in the universe in which curvature does not slow down the velocity? For example, the Acela train, when it goes around a curve, it does not, it tilts into the curve and the velocity stays the same into the curve instead of slowing down, which is like if your car is going to run off the road.
That's a good point. Basically, the short answer is the speed of light is always the same. That at least locally, if you were just sitting outside the sun watching the light beam go by, even if it's being curved, it would still be traveling at 186,000 miles per second. Which is really fast, by the way. The frequency might change, like the amount of energy you observe, but the speed does not change. Now, there are theories, as you alluded to, that says, well, maybe, the speed of light is like a constant of nature. It's just there. And actually, I guess weirdly counterintuitive, and that's how Einstein came up with relativity, actually. So the speed of light's the same for everybody, but to make that work, you've got to have, your clocks have to change rates, and your meter sticks have to change. Anyway, we'll leave that aside. There are theories that at that mysterious T equals 0 moment, or around then, where the laws of physics we know break down. The speed of light is different. And you get issues about what does that even mean, since you use the speed of light to actually calibrate your clocks, but okay. There are theories, but those are completely unproven. I mean, they're speculations, and respecting what people make them, but there's no evidence for it. Basically, when people try to figure out what happened at the very beginning of the universe, there are all these weird ideas, and we can talk about them for hours. And that's one of them. Yeah.
Yes, it was an absolutely wonderful lecture.
Thank you.
And I wonder if you could give us some reference for further reading. I'd love to read the story, the narrative you just offered, you just gave.
Oh, well, I wrote that book.
I mean, you can modestly include your own work.
Yeah, it's called Cosmic Origins, in Mitch Waldrop. It's available on Barnes & Noble, on Amazon. It's not cheap, I'm sorry to say, but I don't have anything to do with price. Unfortunately, I don't have copies here to sell, or I would have bought them. But it is available there, and it tells the story in somewhat more detail.
Could you repeat the name?
It's called Cosmic Origins. And it's written by me and Mitch Waldrop. Yeah.
Does any of this explain the Bermuda Triangle?
No. Which isn't real anyway, so.
This may be, off beat here, but what is fusion energy?
I'm sorry?
What is fusion energy?
Okay. Well, it's, remember I had that slide of the 4 protons coming together to form a helium nucleus? Well, as it turns out, a great many of the light nuclei can fuse. They can merge together. That process, because there's a slight difference in mass, can release a lot of energy. Now, the nuclear reactors we're familiar with, or that exist today, they're called fission reactors. And that actually is sort of the inverse. You take heavy elements like uranium, which is this big, fat thing, do things to it and make that, it's so big and fat and floppy that it can split. And it's just barely hanging together. And you get the heavier nuclei, which have been made in accelerators and so forth. They're even less stable. But when they split, they actually release energy. And that's what happens in a fission reactor. And that's a whole other discussion. Fusion is so that's heavy nuclei splitting into light nuclei. Fusion is the reverse, light nuclei splitting into forming heavy. Now you got to go all the way to the light end of the periodic table. The hydrogen and some of its isotopes, lithium can get in there, and those can merge and release energy. There's a whole lecture about why you can get energy at both ends, but that's what's happening in fusion. You take these light things, protons, the hydrogen nuclei, and merge them together, and there's leftover energy when you do that. And it turns out there's a lot more energy in fusion you can get over to make it work than you can get fission. Yeah, you're next, and then you, yeah.
Does hydrogen turn into helium?
I'm sorry?
Does hydrogen turn into helium?
It does, you know. As I say, that arrow is awfully complicated, but that's essentially, you know, the sum total of what happens. It's, you know, sort of like, you know, you eat food and it turns into us. Something like that, yeah.
Something like
I'm sorry, yeah.
What can you tell us about UFOs and aliens?
There are a lot of stories, and you know, people love to listen to that. But so far as I can tell, there is, despite some provocative photographs, you know, they can all be explained by natural phenomena. Do I believe there's life elsewhere in the universe? Almost certainly. As Carl Sagan used to love to say, you know, if there's not, that's an awfully waste of space up there. You know, those of you who saw Contact, they make a big deal out of that. Does that mean that there are intelligent civilizations sending saucer-shaped spacecraft to visit Earth? I doubt it. I mean, you can't prove it's not true, but every image, every piece of evidence people have trotted out just doesn't stand close scrutiny. In fact, think about it, the number of cameras and the resolution of cameras that are available to people, you know, with these cell phones and so forth, has just exploded over the years. You know, there are cameras everywhere on the planet, and you know, you see video and photos of everything. But the resolution of the photos of UFOs has never gotten any better. They're always fuzzy. They're always sort of. There are whole YouTube channels devoted to not just debunking these things, but explaining in great detail about how you know, these images are almost certainly made. You know, like for example, you see, you know, this sort of weird. You're sitting in an airplane, you see this sort of weird oval floating one, and people take pictures of it. They look like they're called Tic Tacs, because they look like little ovals. Well. You can say, okay, well, you know where the plane was then, you know where it was going, you know what other flights are out there. You can almost, virtually always, if you've got the data, you can always find a plane that explains things. Unfortunately, let's put it this way, profoundly skeptical of UFOs. I think the idea of life elsewhere in the universe is absolutely fascinating. There's a whole rigorous scientific field called astrobiology, looking at trying to understand the conditions that could give rise to life, what sorts of things that might arise elsewhere. There could be life elsewhere in our solar system.
How are they defining life?
There are, I'm sorry?
How are they defining life?
How are they what?
Defining.
Right. Well, that's actually a very interesting question right there. Would we recognize it if we saw it? Life presumably does things like reproduce. It utilizes some form of energy. It metabolizes some sort of nutrients. And it's got to do that because of the second law of thermodynamics, but that's another story. It responds in some fashion to stimuli. Now, the way that we do it may not be the only way to do it. That's kind of doubtful. And the environment in which this happens could be quite different. There are reasons to think that it's probably based on liquid water, but, you know, you can come up with scenarios where that doesn't happen in some other system. Yeah, so we can define life that way. So life could be elsewhere in our own solar system. If you look at what we now know, is that some of the moons of Jupiter and Saturn and even Neptune have subsurface oceans. They're balls of, you know, some rock and this thick crust of ice. It turns out ice is quite common in the outer solar system. But in the interior, just as the interior of the Earth is hot, these things are hot, and so you can have this actually deep ocean of liquid water down there beneath this huge crust of ice. And it's conceivable that life can get started there. And there's a lot of you know, spacecraft being planned and under construction to go out and try to find it. So yeah.
We got one more dummy question.
No question is dumb.
Is the Earth square or round?
It's round.
It's round.
It's actually the Greeks knew that. The people long before Columbus knew that. And how do you know that? Well, you look at the same event in the sky, like, you know, where the moon is at a given time, from different places on Earth, and, you know, just the geometry doesn't work unless the Earth is round. The maps don't fit together unless the Earth is round. So there's just all sorts of evidence that it is round. Also, sit up spacecraft and they hit over. Yeah, anyone else?
I'd like to thank you
Oh, sure.
for this series. I